Let's break down FlashAttention, fast and memory-efficient exact attention with I/O awareness, from Tri-Dow and collaborators at Stanford. Same math as ordinary attention, radically less memory, and a lot faster. Here is the attention matrix. Every token scoring every other token. For a 1,000-token sequence, that's 1,000,000 numbers. Standard attention writes that whole grid out to memory, reads it back, writes it again. FlashAttention computes the exact same answer and never builds the grid at all. Same outputs, to the last bit, but linear memory, and up to 7.5 times faster. The trick isn't a cleverer approximation. It's being careful about where the numbers live. Let's ground ourselves in exactly what attention computes, because every symbol here comes back. You have 3 matrices, queries, keys, and values, each n tokens tall by d dimensions wide, where d is the head dimension, usually 64 or 128. Multiply q by k transpose, and you get the score matrix S, an n by n grid where entry ij is how strongly query I attends to key j. In practice, you also scale it by 1 over root d to keep the numbers tame. Softmax each row of S, turning those scores into a probability distribution, the weights p. Then multiply p by v to blend the values into the output O, again n by d. 2 matrix multiplies with a softmax in the middle. That is all attention is. And the entire performance story lives in that one object in the center, the n by n grid. One more thing worth holding on to. This whole computation happens per attention head and per sequence in the batch, independently. So in practice, you're running many of these little n by n problems at once, which is exactly why the memory cost piles up so fast. Here's the part most courses skip. A GPU is not one uniform pool of memory, it's a hierarchy. At the bottom, HBM, high bandwidth memory, 40 gigabytes on an A100, fast by everyday standards but slow by the GPU's own, about 1.5 terabytes a second. Above it, SRAM, on-chip memory sitting right next to the compute units, screaming fast at 19 terabytes a second, but tiny, megabytes, not gigabytes. Now watch what standard attention does. It computes the scores and writes the whole n by n matrix out to HBM. Reads it back to run softmax. Writes the result. Reads it again to multiply by v. The floating point work is trivial. The time is spent shuttling that giant matrix in and out of slow memory. That is the wall. And that is the paper's central claim. To see why that matters, you have to know operations come in 2 flavors. Compute bound. The clock is set by the arithmetic. A big matrix multiply with a fat inner dimension is the classic case. There's so much math that the memory reads barely register. And memory bound. The arithmetic is trivial, and you're purely limited by how fast bytes move. The telltale is arithmetic intensity, flops per byte. Softmax, dropout, masking. Every elementwise pass over that n by n grid has almost no math per byte, so they're deeply memory bound. Put real numbers on it. Standard attention on GPT-2 does about 67 gigaflops of arithmetic, but moves 40 gigabytes through HBM and takes 42 milliseconds, almost all of it just waiting on memory. The matmls aren't the problem. The grid is. So the obvious question, why write the grid out at all? Why not compute the output directly and skip it? Here's the obstacle that stops the naive approach. Softmax over a row needs the entire row. To normalize even a single entry, you need the maximum across all n scores for numerical stability and the sum of all n exponentials for the denominator. Both are reductions. They couple every column in the row together. You can't finalize any one weight until you've seen all of them. That coupling is exactly why the standard implementation materializes the full row of scores first and why everyone assumed you had to. Break that coupling. Compute the row's softmax without ever holding the whole row, and the entire algorithm falls out. So let's look at softmax carefully, because the fix hides inside it. You never exponentiate raw scores. A score of a few hundred overflows the instant you hit e to the x. So the numerically stable softmax first finds the row's maximum, m, and subtracts it. Then it exponentiates each shifted score, fi equals e to the xi minus m. It sums those into L, and finally divides f by L. Subtracting the max changes nothing in the answer. It cancels in the ratio, but it keeps every exponential between 0 and 1. Now notice what actually carries the information. A whole row's softmax is summarized by just two running numbers, the max m and the sum l. Track those two as data streams in, and you have everything. Here's the key idea, and it's genuinely elegant. You don't need the row all at once. You can process it in chunks and keep the two statistics running. Say the row arrives in 2 blocks. Process the first, local max m1, local sum l1. Now the second block arrives, and it contains a larger value, a new maximum. Problem: L1 was computed by subtracting the old, smaller max, so it's on the wrong scale. The fix is a single multiplication. You rescale the old sum by e to the m1 minus the new max, a factor below 1 that shrinks it to exactly the scale it would have had if you'd known the true maximum from the start. Then add the second block sum, update the max, and you're ready for the next block. Column by column, block by block, you reconstruct the exact softmax denominator, never holding more than one block at a time. The authors put it in a single line. Let's make that exactness concrete, because it's the part people distrust. Take a full row, 6 scores, and stream it in 3 blocks. After block 1, the running max is 3, the running sum is 1.135. Block 2 brings a 4, a bigger max, so we rescale and add. The sum becomes 1.467. Block 3 brings a 5, rescale again, and we land at 1.590. Now compute the softmax the ordinary way, all 6 scores at once. The denominator is 1.590 to the digit. Identical. And here's the storage detail you'll want when you implement it. Instead of keeping the max and the sum separately, fold them into one number. L equals m plus log L, the log sum exp. That single value per row is everything the backward pass will ever need. But the softmax denominator was never the real goal, the output O is. So push the exact same trick one level up onto the output itself. Alongside the running max and running sum, keep a running output vector. When a new block arrives with a new maximum, rescale that running output by the very same correction factor. Then add this block's contribution, its local softmax weights p tilde times its values v. You divide by the running sum only once at the very end. This is the line that makes the whole paper work, so sit with it. The output is assembled block by block, and every time a bigger score appears, everything accumulated so far gets rescaled in place. You never hold the full row of attention weights. Never build a piece of that n-by-n matrix. Just a single d-dimensional vector, corrected as you go. And why is deferring that final division safe? Because the unnormalized output and the running sum scale together. The correction factor multiplies both, so one division at the very end recovers exactly the right weighted average. Keeping everything measured against the running max also means no intermediate value ever overflows. Now translate that onto real hardware, where the blocks aren't abstract. They're chosen to fit SRAM. You can't load the n-by-n grid, but you can load small tiles. Cut the queries into row blocks, and the keys and values into column blocks. Each pairing of a Q block with a K block carves out one small tile of the score grid, BR rows by BC columns. The block sizes are picked so that a K and V block, a Q block, and the running accumulators all fit on chip at the same time. So the enormous n-by-n grid becomes a checkerboard of little tiles, and at any instant the hardware holds exactly one of them in fast memory. Where do those block sizes actually come from? Count what has to live on chip at once. A block of Q, a block of K, a block of V, and the output block O, 4 things, each about BC by D. They all have to fit in SRAM of size M, so 4 times BC times D has to stay under M, which pins the block size to M over 4D. And within that ceiling, bigger is better. The larger each block, the fewer times you sweep over all of Q, and the fewer trips you make to HBM. So runtime drops as the block grows, then flattens once you're bandwidth free or you simply run out of SRAM. That's the whole tuning knob, one number, set by the hardware. Now assemble the full forward pass. There are 2 nested loops. The outer loop walks across the column blocks of K and V, loading each pair from HBM into SRAM one time. The inner loop walks down the row blocks of Q. For each tile, entirely on chip, compute the scores, Q block times K block transpose. Take the tile's row max, exponentiate, row sum, its local statistics. Merge those into that query block's running max and running sum, using the correction factor from before. Then update the query block's output in place. Rescale what's there, add this tile's weighted values. Write back just the output block and its two little statistics, and move to the next tile. Because K and V are the outer loop, each query block's output gets revisited and refined as new key blocks arrive. And that loop order is deliberate. K and V are what you reload into SRAM. So keeping a pair fixed while you stream all the query blocks past them minimizes how often the large matrices have to cross the memory bus. When both loops finish, O is exact, bit for bit what standard attention would give, and the n-by-n matrix never once touched HBM. If you want to actually write this, here is the entire forward kernel. Initialize the output and the two statistics in memory. Outer loop over the K and V blocks, load one pair into SRAM. Inner loop over the Q blocks, load the query block along with its running output and stats. On chip, the tile scores, its local max, the exponentials, the local sum. Update the running max, and then, this line, in green, apply the correction factor to rescale the old sum and the old output before adding the new block's contribution. Divide by the running sum, store the block and its two statistics, and continue. That's it. No n-by-n array is ever allocated. 13 lines, and it produces the exact same attention as the textbook version. One implementation detail ties it together. In standard attention, each step is its own GPU kernel. Matmul, write to HBM, softmax, write to HBM, matmul, write to HBM, 3 separate round trips through slow memory. FlashAttention fuses all of it into a single kernel. Load the blocks once, do the first matmul, the softmax, and the second matmul entirely on chip, and write the result out one time. That fusion is only possible because tiling shrank the whole computation down to fit in SRAM in the first place. Now let's actually count the memory traffic, because this is where the payoff becomes a theorem. Standard attention touches HBM on the order of n squared. It writes and reads that whole grid several times over. FlashAttention, each K and V block is about the size of SRAM. M. For every one of those blocks, you sweep over all of Q. That's roughly ND over M passes over the queries, and each pass moves about ND numbers. Multiply it out, and you get n squared d squared over M total HBM accesses. Since d squared is much smaller than M, d is around 100, M is around 100 kilobytes. That's many times fewer accesses than n squared. And here's the part that breaks people's intuition. FlashAttention does more floating point work, 75 gigaflops versus 67, because it recomputes in the backward pass. But its memory traffic collapses from 40 gigabytes to 4. Attention is memory bound, so traffic is what counts. More math, a fraction of the shuttling, and it runs nearly 6 times faster. It also uses linear memory instead of quadratic, because the grid is never stored. And the authors go one step further and prove a matching lower bound. Across the relevant range of SRAM sizes, no exact attention algorithm can beat this HBM count asymptotically. So FlashAttention isn't merely faster. On memory traffic, it's essentially optimal. And this is proven, not just measured. One more thing you'll need for real language models: causal masking. A token can only attend to the past. So in the tiled picture, every block above the diagonal is pure future, and you simply never compute it. That's roughly half the tiles gone, for free. The blocks sitting right on the diagonal are the only subtle case. Part of each is past, part is future, so you mask the future entries to -infinity inside the tile, on chip, before the softmax. Sliding windows, block-sparse patterns, they all slot into this exact same loop. If watching a memory access argument turn into a 6x speedup is your idea of a good time, like, subscribe, and send this to the friend who still thinks fewer flops automatically means faster. Because the backward pass is where it gets even better. Training needs gradients, and the textbook backward pass needs S and P, the exact n-by-n matrices we so proudly refuse to store. Awkward. The answer is recomputation. Remember, In the forward pass, we did save two things per row, the output O, and that single log sum exp number, L. It turns out that's enough to rebuild any tile of the scores and probabilities on the fly in SRAM during the backward pass. Recompute the tile, use it, throw it away. This looks like gradient checkpointing. Trade compute to save memory, but there's a twist. Recomputing a tile in fast SRAM is so much cheaper than a round trip to slow HBM that you don't actually trade. You save the memory and you come out faster, both at once. And the gradients themselves are cleaner than you'd fear, just the chain rule, done by hand. The gradient of V is P transpose times DO. The gradient of the weights, dP, is DO times V transpose. For the scores, softmax has a known Jacobian, diagonal of P minus PP transpose, which gives ds equals P, elementwise times, the quantity dP minus D. And D is the trick that keeps everything linear. Instead of forming a full n-by-n product for each row, it collapses to a single scalar, the row sum of DO elementwise O, which is just DOI dotted with OI. One number per row. With ds in hand, the input gradients drop right out. dq is ds times k, and dk is ds transpose times q. Every one of these is a matmul over tiles, no n-by-n array anywhere. And here's the backward pass as a loop, the same shape as the forward, run in reverse. Outer loop over the k and v blocks, inner loop over q. First, recompute this tile's probabilities, the scores from q and k, then p as the exponential of the scores minus the stored L. That one line stands in for the entire n-by-n matrix we chose not to save. Then accumulate. The value gradient gets P transpose times DO, compute dP, and that cheap little d, the row sum of DO times O, form ds. And push out the input gradients. dq gets ds times k, dk gets ds transpose times q. Each block's gradients accumulate across the loop, everything stays linear in memory, and you get exact gradients, without ever materializing the attention matrix. In their words. And once attention is tiled into blocks, sparsity comes almost for free. Hand the algorithm a block mask, which tiles are even allowed to matter, and simply skip the 0 blocks. No wasted compute, no wasted memory traffic on them. The I/O cost drops by exactly the fraction of blocks you keep. That's Block-sparse FlashAttention. 2 to 4 times faster again on top of everything, and it scales attention out to 64,000 tokens. So does the whole contraption earn its keep? BERT Large trains 15% faster than the standing ML-perf speed record. GPT-2 trains up to 3 times faster than the common implementation, and crucially, the perplexity matches to the decimal, because the computation is genuinely identical, not an approximation. The long-range arena benchmark speeds up 2.4 times. Memory that used to grow with the square of the sequence length now grows only linearly, so context windows can finally stretch. And that unlocks new capability. For the first time, a transformer clears better than chance on path X at 16,000 tokens, and Block-sparse pushes that to 64,000 on path 256. Not by approximating attention, by respecting the memory hierarchy. For the record. So here's the whole recipe. The n-by-n attention matrix is the cost, so never build it. Stream the softmax using 2 running statistics, the max and the sum. Tile Q, K, and V so a block fits in fast SRAM, and fuse everything into one kernel. Rescale the running output every time a bigger score shows up. And in the backward pass, recompute the tiles instead of storing them. The result is bit for bit the same attention, in linear memory, running far faster, because the bottleneck was never the math. It was the memory. The one-line version. Attention was memory-bound, not compute-bound. So FlashAttention keeps the whole computation in on-chip SRAM, streams the softmax with 2 running numbers, and never writes the n-by-n matrix to slow memory at all. And it leaves you with a thought. How many other slow algorithms aren't compute-bound at all, just badly acquainted with their own memory? That's my read. Tell me yours. Until next time.